rational functions. Rational functions, you know, the kind of the calling card that they're going to use is R of X, just for rational. I don't know why they. But you got P of X over Q of X. It really doesn't matter what those are. They're just functions. It's a function on top. It's a function on the bottom. That sort of thing. And there's some things that we've got to look at in order for something to be a rational function. And one of those things is the domain. Okay. Domain of rational functions. You've actually already done this some. Just you had fairly simple rational functions when you did this. If we're going to state the domain, we did this back in chapter 3, I believe. And we had a function, fairly simple function. Maybe it was x squared minus 4 over x plus 5. So this is a lot like one that we've done in chapter 3, I believe is where it was. What's the red flag that's raised here? X in the denominator. So that's the red flag for domain. So how do we find the domain if there's an x in the denominator? Set it equal to 0. Set the denominator equal to 0. X plus 5 equal to 0. And solve it. You know, this one's not a large polynomial, so it's just not using the skills that we just learned, but it's the idea that, you know, it's the process that we're after here. X equals -5. So that means x can't be -5. So let's write that domain in a collegiate way, which would be interval notation, right? So I'll write it in set notation. X does not equal -5. What's the interval notation for that? Kind of gotten away from that this chapter, so we're probably going to be a little bit rusty on it, but is it a bracket? No, because we're not including the -5. We're skipping it, right? U and then -5 to infinity. Okay, so we're a little rusty on that. We haven't been doing that much this chapter, so we're going to get back into that this during this section. Okay, so setting the denominator equal to 0. This one happens to be a linear piece in the denominator, but that's the idea here. We're going to get to some that are not linear pieces in the denominator. They're higher degree polynomials like what we've been solving. Okay, so let's get to one of those. Example B. Let's say we have this function g of x, and it's maybe x plus 5 over x cubed plus 27. Sure. Now that's a higher degree polynomial. It's a little short, but it's a higher degree polynomial. So again, we look for domain of this. What's the red flag that's raised? X in the denominator. So that we've got to take care of that. So to take care of that, we set the denominator equal to 0, and we're going to solve it. Now, how do we solve x cubed plus 27? What are the ways that we could use to solve that? Well, cubic root would get us one of our answers, but we'd lose a couple others. Think about how we solved all those polynomials this last couple of days, last 4 days. Find all the zeros. That's exactly what we need to do. So what are my options for finding the zeros? I can graph it, and that's going to help me get started. And then I can do synthetic division. How many people know that that'll factor? Not quite. Close. X plus 3 is part of it, but not the x minus 3. It's a difference of, or it's a sum of cubes is what that is. And that would be x plus 3 and then x squared plus 3x plus 9 is how that factors. Sums and difference of cubes. It's a pattern, really, basically learn to do that. The other way of getting that factored form of that would be, if you did synthetic division. Trying to pull the skills that we've been working on. They're used to do this. If this is a polynomial that's got other terms in there, that's probably what I'm going to have to do. I just happen to know that factors. Not every one of them will factor. So, here we're going to run a -3, 1, 0, 0, 27. That'd be -3. Excuse me, that's supposed to be a minus sign right there. Forgot to change the sign. And then that'd be 9. And then that's -27. And that's where that factoring could come from doing a synthetic division. Okay. Now, once I get here, I can get my zeros by setting those equal to 0. We've got a quadratic here, so I could use quadratic formula to see what kind of answers that has. And that's what I would do. I'd say that x plus 3 equals 0. So x can't be -3. That's one of my things in the domain that's going to be a problem. When I said x squared minus 3x plus 9 equal to 0, it won't factor. Nothing multiplies to be 9, it has to be -3. So I'm going to try the quadratic formula. 3 plus or minus 3 squared is 9 minus 4 times 9 times 1, which would be 36. So 9 minus 36 underneath there. And then 2 on the bottom. So what do we know about this right now?
It's going to be negative.
That square root is going to be an I. So is that going to mess up our domain? Think about when we were doing these, there were some that y'all had problems with, and these were ones that were like this. If it's imaginary, it doesn't show up on the graph, remember? So that right there, because that's going to be a complex answer, we know that that's not going to mess up our domain. Okay, so we don't have to go ahead and finish that. We could to get the zeros of it. That's good practice. But because that's complex, it's not going to be a part of the domain. Okay, so when we state the domain of this, what's the only thing x can't be? -3. Now, technically, it can't be those complex numbers that are here, but again, they don't affect the domain. The domain we're talking about is going to look on the graph kind of thing that we're going for here. So, interval notation for that. Yeah. There's our domain for that rational function. Okay. Let's go to this one. Maybe we have f of x is equal to x squared plus 4 over x to the 4th power plus 13x squared plus 36. We want to find the domain of that. So if we're going to find the domain of that, what do we have to do? Set the denominator equal to 0, right? Solve it. Okay, so that's what we're doing. Now, I'm thinking, okay, it's 4th degree, so graphing it might be an option. So I'm going to graph that, see if I can find somewhere where it crosses the x-axis. X raised to the 4th plus 13x squared plus 36 graph. Dun, 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 dun. It'll show up on my regular window. I'm going to zoom out a little bit. Just, from the origin there. So I can get some of the picture. There it is. It's way up there. It's barely there. You can barely see it, but it's there. What's going on here? Is it crossing the x-axis? No. So that means that there are no real zeros to that. Remember? Because we talked about that when we're solving polynomials. If it's a real 0, it's going to touch or cross the x-axis. This one doesn't touch or cross the x-axis. So are there any restrictions on the domain? No. So what would the domain of this rational function be? Good. Now, technically, if you were going to have to solve that, since we kind of struggled with this one yesterday, and then there was one on the test that could have been done this way too, or one on the quiz that could have been done this way, you could factor that like you would a trinomial. What multiplies to be 36 and adds to be 13? 4 and 9. So it's x squared plus 4, x squared plus 9. And we'd get plus or minus 2i from that factor and plus or minus 3i from that factor. So there are 4 zeros to that. They're just not real zeros out of that. Now, being able to factor that's going to be important when we start going to the next thing with these rational functions, which is pretty important to be able to factor that. So I wanted to show you how to factor that, make sure we were on the right track for that. All right. Let's talk about the rest of it. Okay. Now, with these rational functions, there's a few things that can happen. There's these things called asymptotes. A-S-Y-M-P-T-O-T-E. Asymptotes. Boundaries. There are things inside the graph. When we go to graph a rational function, these asymptotes show up, and what they are, they're boundaries or kind of border lines. They're going to be, we're going to draw them as dotted lines that show the restrictions on the domain on the graph out of that. And what happens with these is there's 3 different kinds of asymptotes. One of those is a vertical asymptote. I'm going to change that from zeros to factors. That's a better way. Okay, vertical asymptotes, they come from the factors of the denominator and consequently the zeros of the denominator. Now, the only time that's going to be different, the denominator, we factored the denominators to find the domain. So when we do that, it can help us find the vertical asymptotes. It's kind of like a 2-for-1 deal. All right. So with vertical asymptotes, though, there's times where your domain may say that 2 is left out and maybe positive 4 is left out. Well, there's times where both of those won't be vertical asymptotes because the rational function might actually simplify. So we've got to look at the factored form of the numerator and denominator and see if it simplifies some for us when we start talking about vertical asymptotes. Most of the time, though, they're the same thing as what your x can't be for the domain. You just got to look and see if it simplifies. It's kind of like any kind of fraction. You got to look and see if it'll reduce anyway. Every time before you state something about it, you got to reduce your fractions. So we're going to look at that. Vertical asymptotes, they're coming from the denominator, and that's where we're going to find those. Now, the other 2 are dependent upon what kind of problem you have. Okay, vertical asymptotes are always going to do that, come from the denominator of your fraction. The horizontal asymptotes, they've got some conditions. Okay, now when I say degree, what am I talking about? Yeah, highest exponent on the numerator And then if I say the degree of the numerator is this, it's the highest exponent in the numerator. Degree of the denominator is a certain thing. It's the highest exponent on the denominator. Okay. So if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0. Doesn't matter how much less it is. We could have an x to the second power on top and an x to the fifth power on the bottom, and that's still less, so it's y equals 0. We could have an x to the first power on the top and an x to the second power on the bottom. It's still going to be a horizontal asymptote at y equals 0, always. Okay, if the degree of the numerator is less than the degree of the denominator. Okay, that's one condition for a horizontal asymptote. The other condition would be if the degrees are equal. It's a horizontal asymptote at the ratio of the leading coefficients. And we're going to see some examples of this in just a little bit. So you'd have something like y equals a over b, something like, it'd be a fraction there, reduced fraction if it needs to be, okay? Ratio of the leading coefficients if the degrees are equal, okay? So degree of the top is less than the degree of the bottom, then we got a y equals 0 horizontal asymptote. If the degrees are equal to one another, then we have a horizontal asymptote at the ratio of the leading coefficients. Okay, so that's the conditions for horizontal asymptotes to exist. They don't have to exist. They sometimes do. Vertical asymptotes, if it's a rational function, they're going to exist. Horizontal asymptotes don't always exist. Sometimes, instead of horizontal asymptotes, we will have what's called an oblique. O-B-L-I-Q-U-E asymptote. You'll sometimes hear me call this a slant asymptote, because that's what we called them when I was growing up. They decided oblique sounds like you're smarter, so that's why they started calling them that, I guess. Can't really understand any other reason to call them oblique. Oblique asymptotes or slant asymptotes, they're slanted. A vertical asymptotes goes straight up and down. Horizontal asymptotes, obviously horizontal. Oblique asymptotes are slanted. That's why we called them slant asymptotes when I was going through college algebra in high school and stuff. So, all right, when do they happen? They happen if the degree of the numerator is 1 more than the degree of the denominator. It can only be 1 more. So you could only have like an x cubed over an x squared. If it's x to the fourth on top, the bottom has to be x cubed for an oblique to exist. Okay? If it's x to the fifth over x cubed, it's not oblique. Okay? That's no horizontal or oblique. It's possible that you don't have horizontals and you don't have obliques. You very likely will have vertical ones, though. Okay. Most of the time, you're going to have vertical ones. Oblique asymptotes are going to be in slope-intercept form. That's what makes them slanted. It's a straight line. All our asymptotes are going to be straight lines. You never have an asymptote that is a curved line. It's contradictory to the idea of an asymptote. All right, so if the degree is anything else happening, numerator compared to denominator, then you just don't have the oblique or horizontal. You will never, and this is pretty important.
Hunter Brown, Andrew White, report to the office.
Horizontal and oblique never occur together. They can't. Because horizontals are only going to happen if the numerator has a smaller degree than the denominator or that the degrees are equal. That's the only time horizontals occur. Obliques occur only when the degree of the numerator is one more than the denominator. You'll never have those two together. Never have obliques and horizontal asymptotes together. Let's look at some functions. See if we can check out what's going on here. I don't know what letter we're on. D. All right. We're going to state the domain and asymptotes if they exist. All right. So here's our function. F of x is equal to, let's do x squared plus 7x plus 12 over 4x squared minus 1. All right. So if we're going to state the domain and then the asymptotes, so we're going to have the domain, and right there with that, I'm going to get the vertical asymptotes. And then I want to do horizontal if they exist, and then oblique if they exist. So I'm just kind of doing this. On quiz for this, I'm going to ask you for one of those things. But you may have to go through 2 or 3 of them to get one of them. Okay, so domain, let's get that first. Okay, so 4x squared minus 1 equals 0. How can we solve that? A couple of different ways, a bunch of different ways, actually. It's quadratic, so we can do square roots. Or I could factor it. I think I'm going to factor it. If at all possible, I'm going to factor. The reason I want to do that is because of the vertical asymptote stuff, where we could lose part of the denominator if the fraction will simplify. So the factored form of the denominator would be what? So that's a difference of squares. And I'm going to go ahead and factor the numerator too. What's the factored form of the denominator? Oh dear, this is not good. We don't know that. 2x plus 1, 2x minus 1. And then can we factor the numerator? Let's go ahead and factor it while we're in the factoring mood. Multiply to be 12, add to be 7. X plus 3, x plus 4. So when we look at that factored form, we want to look at the factored form of the rational function to see if stuff is going to cancel. And nothing's going to cancel on this one. So whatever we find for the things that x can't be in the domain, that's going to be our vertical asymptotes. Well, our vertical asymptotes would be, or our domain restrictions are, x can't be negative 1/2 and x can't be positive 1/2, right? We set those two factors equal to 0. That's where that's coming from. And then, so our domain is x such that x is not equal to plus or minus 1/2. And let's write it in interval notation because we're smarter than that. So how's it go? negative infinity to negative 1/2, union, union. Good job. Infinity did look too good there. Okay. So there's our domain. That's done. Now our vertical asymptotes are going to, since nothing canceled in the factored form, again, you want to try to factor everything and see if you can get stuff to cancel, because that's going to cut out some of your asymptotes. Okay. And so our vertical asymptotes, since nothing's simplified, they're going to match up with these things. They're going to be at x equals negative 1/2 and x equals positive 1/2. We'll relate that to the graph. Let's graph that original function first. And let's look and see what your calculator shows you. So I'm going to hit zoom 6 to go back to my normal window. And then y equals. All right, calculator, y equals. All right, now be careful that you put the numerator in parentheses. So we got x squared plus 7x plus 12, close the parentheses, divided by parentheses 4x squared minus 1. And hit graph. It's funky. Now, we've got some stuff happening here. See how it turns down there? That's what tells you there's a vertical asymptote happening. Okay. See how it's kind of, like this? That's going to tell us that there's a, make sure I didn't get the squared on the 4x. That's the problem. That's why it's not looking like yours. You're going to be looking at me like I got pink hair or something. I guess that's not too weird nowadays, but it used to be weird. Minus 1. Now, let's graph that thing. There we go. All right, so we see here now it's a little bit more like it should be. We got a negative 1/2 vertical asymptote. Your calculator doesn't draw those. Understand that. But there is one here at negative 1/2 and then one here at positive 1/2. You see how the graph turns up there. It approaches negative 1/2, but it doesn't cross it there. So we find those things. That's what's going on. Now we look at it and we say, okay, horizontal or oblique. So we got to look at the degrees. What's the degree of the numerator? 2. What's the degree of the denominator? They're equal, so that means there has to be what kind of asymptote? I heard 2 different answers. Horizontal, because they're equal. And if they're equal, the horizontal asymptote is going to be where? At the ratio of the leading coefficients, if they're equal. What's the leading coefficient up top? 12. The leading coefficient's 1. Leading coefficient on the bottom is 4. Leading coefficient is the number in front of your term that decides the degree. Okay. So there is a horizontal asymptote at y equals 1/4. Y equals 1/4. If there's a horizontal asymptote, what do we know about oblique asymptotes? There won't be any. Remember, horizontals and obliques never occur together. Okay. Never occur together. All right, not bad. Let's look at the next one. Let's say here's our function, g of x is equal to 3x to the 4th power minus x squared over let's do x to the 3rd minus 8.
oblique.
If we are going to have an oblique, why?
The numerator is one more.
The degree of the numerator is one more than the denominator. So we know we're going to have an oblique. It means we don't have a horizontal. So we got to find the domain and the verticals as well. So we know that stuff's coming up. So let's go ahead and find the factored form of each of these. So the numerator could factor with the GCF of x squared. That leaves 3x squared minus 1. So there's the factored form. And then on the denominator, that's a cubes, difference of cubes. So how does that factor? Maybe you didn't learn this in Algebra 2. So I'll teach you how. What cubed is 8? 2. It's going to have a short piece and a long piece. The short piece is always the same as these. So it'd be x minus 2. The long piece is a quadratic. You use one of the x's, so you got an x squared left over. And then you used one of the 2's, so you got 2 of them left over, so that's 2 squared, it's 4. That's always a plus sign on the end. The middle term, 2 times x. And then the sign in the middle there is always the opposite of what the problem had. If it had a minus sign, it's a plus in the middle. So there's the factored form of that thing. We want to look at factored form. We've been doing a lot of factored form. Every quiz, we've done write me the factored form and the standard form for that. This is part of the reason, because we need the factored form to help us there. Now, does anything cancel out? No, but we need to check for that every time, whether it cancels out or not. Having it in factored form, though, really helps us in solving for our domain and getting our vertical asymptotes out of that. Anyway, so domain. I'm setting x minus 2 equal to 0, and that's going to give me x equals 2. So x can't be 2. And if I set x squared plus 2x plus 4 equal to 0, what do I know about that? Can't be factored. So I'm going to think, what's the discriminant of that? So that'd be 2 squared minus 4 times 4 times 1. That's 4 minus 16, which is negative. So that's what's under the square root when we do. So it doesn't matter for domain. That's right. So doesn't even matter. So the domain, all x's such that x does not equal 2. Oops. And let's do the interval. Negative infinity to 2, 2 to infinity. Well, my 2 didn't look like a 2 there. There's my domain. Since nothing canceled out, my vertical asymptotes are at x equals 2. The one with the complex solution is not going to show up. Remember, it doesn't show up in the normal graph.
So now we just graph it.
No, that's where the oblique, we've got to do some work to get the exact oblique asymptote, because you told me it's going to have an oblique, right? So we know over here under my horizontal, I can put none. For the oblique, though, because the degree of the numerator is one more than the degree of the denominator, then we're going to have to do long division. This is why we did it. Okay, synthetic is wonderful, but it doesn't work for this unless we're dividing by a linear piece. And we're not dividing by a linear piece. We're dividing by x cubed minus 8. So this is why we had to do long division before. Told you we'd use it. This is it. Or this is one of the places where we use it. So if I'm going to divide by x cubed minus 8, I'm going to put 0x squared in there, 0x, and the minus 8. And that's dividing into my numerator, which was 3x to the 4th, 0x cubed minus x squared, 0x, and then a 0 constant term. So I'm putting a representative in there even in what I'm dividing by, it really makes my life easier when I do that. If I put a 0x squared and a 0x in the x cubed minus 8, and then into the 3x to the 4th minus x squared, I put a 0x cubed, a 0x, and then a 0 as the constant there. Just filling in the gaps. And then I'm just going to do my long division. And what's going to happen is we're going to get a linear quotient because the degree of the top is 1 more than the degree of the bottom. Slant asymptotes are linear. They're slope-intercept forms. So, or oblique asymptotes, sorry, used the wrong word, knew it would. What times x cubed gives me 3x to the 4th? 3x. Distribute. 0x cubed. 0x squared. And then negative 24x. Subtract. That's 24x plus 0. What times x cubed is going to get me 24x? Nothing, right? So, hold on. What did I do wrong? 3x to the 4th, 0x, or x, 0x squared,
Cindy Scudder and Carol White report to the office.
negative 24x. Okay. Yes, that should be negative x squared. That's why it's not working. All right, let's get that finished up and then y'all can go. We'll finish this up tomorrow, but let's finish this problem. That would give us plus, well, not plus. We don't get anything out of that. Let's finish this tomorrow. We're going to finish the lesson tomorrow. We got several more examples here I want to do for this. So we'll finish this up tomorrow, and depending on what time that is, we'll go from there, okay? You guys have a good day, and enjoy a day with not having to work.